So this lecture will discuss about all the things we learned in the perturbation theory to understand a real problem, which is a problem of a single electron atom, and mostly we'll focus on hydrogen atom, and we'll try to see how perturbation theory helps us to understand certain things about like its energy level and states, and also how does it nicely correlates with the experiments. And it is one of the major triumphs of perturbation theory is to predict spectral lines of atoms which are very precisely measured in experiments, and perturbation theory can explain it very precisely, and that is a, so this is a very serious section in that sense, and it's also very what will I say, it's not conceptually difficult, but it has lot of calculations and lot of tiny tricks here and there and lot of approximations. So I would it's the most I would say it's the most technical section so far, and I would say that you again as usual like go through every step, every equation by yourself, see what does it mean and understand, otherwise it is not at all, it will be not at all easy to follow this section. Okay, so with that introduction, let me start with the corrections of energy levels of hydrogen atom by various perturbative effects. So the hydrogen atom here is given by this equation 1, which is h p square by 2m plus Vr is the part which we have already studied in great detail in quantum mechanics 1. So Vr is basically the minus Z square by E, which is the Coulomb term from nucleus, the Coulomb interaction between nucleus and the electron. For a general nucleus of atomic number Z, it's Z squared by R, but here we will be mostly interested about hydrogen, so the Z is 1. So now there is the relativistic correction terms are given by this HRK, which is coming from the relativistic kinetic term. The spin orbit coupling, which HSO, which comes from comes from the fact that in the rest frame of electron, the nucleus or the proton is moving is a moving source of electric field, so it produces a magnetic field by relativistic effect, and then you can that magnetic field interacts with the spin of the electron, which is termed as spin orbit coupling. And then there is another term which comes from uncertainty, and it's called it's the Darwin term, and actually this a full treatment and proper treatment of this term involves Dirac equation. So I will not discuss this term in detail, but I will discuss to some extent the first two terms. So what is the first term? It is basically the relativistic correction of kinetic energy of electron, which is given by m square c to the 4 plus p square e square square root minus mc square, the rest mass of electron, where m is the rest mass of electron, this is the rest energy of the electron. So in the non-relativistic theory, of course, you take only the first part, and in the relativistic theory you take the second, you take the full thing. So if I expand this term by taking the p square by c square as my small parameter, or v by c as my small parameter, this expansion looks like this, and if I keep the only first term of this expansion, so the kinetic energy looks like this: p square by 2m minus 1 by 8 p to the power 4 by m cube c square, which that is an approximation which is valid only if the kinetic energy of the electron is much less compared to the rest energy of the electron. And it is usually true, that you will see, because the velocity of the electron is not like speed of light or something, so you can show that this is a correct approximation. So that is the form of my kinetic energy. So that is also the first significant term in the kinetic energy after the non-relativistic expression is this term. So let's look at the scale of this term, like how is it really a small term or it's a big term, so whether we can treat it perturbatively or not. So we have seen that the perturbative constant or the perturbative quantity here was this v by c. We took the v by c square, but this is basically the physical quantity which is appearing in this perturbative expansion as the small parameter. So what is this quantity? If I take the Bohr first orbital formula, so the v is given by e square by h bar c. So now it is expressed entirely in terms of constants. So for Bohr model, I can plug in the number and I get this number 1 by 137 roughly. This is called the fine structure constant. and it's a, you can say it's a conspiracy of nature probably to have this number to be that small, such that the perturbation theory is beautifully applied here because of this small parameter character, and you will see that how remarkably good you can predict everything. So, because of being the velocity of the electron in the first orbital to be such a small quantity compared to c, and that appears naturally as a perturbative quantity in this theory. So, not necessarily you will get such a small parameter always in all the problem you will do in future in some research work or something, and it is one of the art to write the problem in a clever way such that clearly a physically meaningful small parameter emerges of the theory, and that is often one of the most challenging part. So, this quantity basically also quantify the gap in the so these relativistic corrections are called fine structure. These are called fine structure prediction, because you will see that in the first order correction they appears as alpha square, as we expanded in alpha square. All other terms are also alpha square. The next order correction they come as alpha to the power 4. They are called hyper fine structure. So, this one requires much more sophisticated instruments which were discovered later, but these are the fine structure corrections were discovered first in the experimental. And it was like the famous Michelson-Morley, who was the master of ultra precision measurement and optics. So, he was the person who first measured this fine structure spectra in hydrogen. So, with this constant, so now we establish this constant is small constant. So, now we can also find the correction of this relativistic kinetic term and the E naught, the natural the lowest ground state energy of the hydrogen atom by Bohr theory. This ratio is v square by c square, which is order of 10 to the power minus 4. So, that tells us that the first order perturbation theory is going to be pretty good, whatever we are going to do here. So, let us proceed and now look at the correction this term gives you. We simply know that we can apply this formula of first order perturbation theory formula here, first energy correction. And since we know that this term only contains momentum and that has nothing to do with the spin eigenstates, so we can drop the spin quantum number from this description, which comes as ms. So, we ignore the spin level just from here for time being. So, this is my unperturbed Hamiltonian E naught NLM En, which is the hydrogen atom states. NLM is unperturbed, and we know that En basically looks like this. It is 1 by n square with some constant m to the power 4 2 by 2 h bar square, and if I write A naught as the Bohr atom radius, I use the formula for that. It looks like this. It's a nice compact form. So, now let us plug in and calculate this quantity. So, this is something straightforward. You can calculate it very simply by writing the hydrogen atom wave function and operate del square on it, because p is nothing but del square, proportional to del square is some constant. But that is a little hard calculation, like lengthy calculation, probably also have to involve spherical function. But there is a little cheaper way to do that. The cheaper way is that you write this h naught as p square by 2m e square by minus square by r. So, p square is basically 2m times h naught minus e square r. So, that is the quantity. So, p square, p to the power 4 is square of that. So, you expand the square and you get these two expectation values, which are relatively easy to calculate in hydrogen atom. And you just plug in the hydrogen atom functions, you will get this number. There is actually another easier way to, because later you will need much more of this 1 by r, 1 by r square, 1 by r cube, 1 by 2 to the power 4. There is a systematic way to do that, which is pointed out in Shankar, how to do this once you know one of that. And there is also another thing called Feynman-Hillman theorem, which allows you to calculate this kind of 1 by r expectation value in LM much more simply. But I would suggest you to go through this from the book of Griffiths or any other book, that, and or just try by yourself, that if you put down the NLM wave function, what is this 1 by r expectation value. So, 1 by r square expectation value you can similarly obtain like that. You plug in these quantities and this is the form you get. This is the first correction, relativistic kinetic energy correction. Notice that it is an order alpha square correction, and this is basically just that tells you that how much the first energy of the energies of the hydrogen atom will shift because of this relativistic correction. Okay. Now that we got this up to this, so let's see the next correction, which is spin orbit interaction, which is also a relativistic correction. So which appears because so normally the nucleus doesn't produce any magnetic field. I mean, it produces because of the nucleus spin it can produce, but let's say we just have a proton and it has only an electric charge, so it produces an electric field. But if you think it from the point of view reference frame of the electron, then it sees a electric charge which is moving, and we know from that produces a moving electric charge produces a magnetic field. So what is that effective magnetic field? We know this from this form is the magnetic field is 1 by C V cross E, and the electron is subject to now the Coulomb field due to proton, which is basically this electric field, and also which is this electric field, and also the velocity of the proton on this rest frame, and that together produces an effective magnetic field which the electron sees, and that magnetic field is given by minus E by CR cube V cross R. So what is the interaction of this magnetic moment of electron, which is a spin magnetic moment, with this magnetic field? So here is a pictorial representation of that. This is the proton and this is the velocity of the electron and in the nucleus. Now in the reference frame of the electron, the velocity is minus v. So then it sees the proton is moving around and it is producing this orbiting charged object produces a magnetic field here, and that magnetic field, by the way, in all these approximations we are doing, we assume that the electron, like the nucleus is a static object, but in the reference frame of electron, of course it is not. So here it is, this is the magnetic field it produces here, and we know that if there is a current in a loop and the current is given by I, which is I, you can think it as the current produced by the moving proton, it produces a magnetic moment, and that magnetic moment is given by, let's say, L, and why it is L? Because it is of order r cross b, it's like a angular momentum, and the spin of the so the magnetic moment of the electron, so the energy of this system will be the magnetic moment of the object at the center, which is, let's say, magnetic moment mu, and dot the B, the magnetic field produced by the charge or the current around that, which is in this configuration is given by mu 0 I by 2r, and where L is equal to L. So now the spin orbit coupling, the Hamiltonian contribution for this, so we call it spin orbit coupling because it's like an orbital angular momentum, because of the object orbiting around the electron orbiting around the nucleus. And if I write down all this formula, it looks like this, and V cross R is singly angular momentum, so it will look like this. And we know that the if mu is the magnetic moment of electron, that is given by E by mc, the spin of the electron, the magnetic moment due to spin. So when I plug in this form inside this, I will get this form. So this is my spin orbit coupling. So E square by m square c square r cube L dot s. What is the we want to evaluate the effect of this term? We will sandwich it with the simple formula between NLM, and we have to evaluate this 1 by r cube. Again, look at Shankar, this 17.3.4, they discuss how to calculate this kind of quantities. So when you plug in this formula, you will get this m cube e to the power 6 by h to the power 6 1 by n cube L plus 1 L plus half. So now we know this part. Now let's look at how this part contributes. So this part we can write, now recall that the total angular momentum is basically L plus L s square. So j square is L plus s square, and I expanded this in this way, square plus 2 ls, such that L dot s can be written in terms of the j and L angular momentum, j square L square angular momentum. Now it is very convenient to work in this basis of j square, jz, L square and L square, because these are the terms which commute with the Hamiltonian. So in that basis things will be like L dot s, commute to the Hamiltonian means the L dot s Hamiltonian, because that way that the Hamiltonian will be diagonal in that form, and then it will be very easy to deal with the calculations of that. And so now we will write everything in terms of these basis. So you will see one of these thing again and again in different problem, different perturbations. You will see it's not always the easiest to work with one particular basis. So you have to, depending on the term what it is commuting with, you work in that basis, then the term becomes easy to evaluate, and then you use Klebs-Gordon coefficients and all that to go back to the other basis, and like you can choose your basis and you know how to go from one basis to another basis by the Klebs-Gordon coefficient. So the first order perturbation theory will say, so now we establish that because of this commuting form, we will write it in terms of this L j squared jz L square L s square basis. So it is because nj L s nj in this, the wave function is written like that. And now the spin term is important, we cannot drop the spin level which you did earlier, because now we are dealing with directly with the spin contribution, the L dot s term. So now I plug in this HSO. We know L dot s is basically this. It's very easy to calculate this effect of this j square on this and L square and s square, because of this I have written it in this basis. So that will be just this, that will be just the contribution. Then we will be left over with the 1 by r cube, which we showed how to calculate the 1 by r cube term. Now we know that for every L there are two possible j's, which is L plus minus half, because the spin is half, because it's L plus, it will be basically all the terms L plus s to L minus s, and that will lead to this form. So for j equal to L plus half, you will get this form, and j equal to L minus half, you will get this form. Now you can write this whole complicated prefactor, simplify it in terms of the energy states value of the hydrogen atom, which is En. You know that is basically minus 13.6 by n square electron volt if you plug in these numbers. So we simplify this in the form of En, fine structure constant, n square and n. So when I plug that, I write this in this form, it looks like this equation. Now I can more conveniently go to write it in terms of the j, because j is a good quantum number of this problem. So I write it in this form. So when j equal to L by 2, it is this, and j equal to L minus half, L plus half and L minus half, this is the form. So basically if I simplify the algebra, so that is what it becomes. So the first correction or is because of spin orbit coupling, because comes of this from. Now recall, it was, what was it for the relativistic kinetic energy correction? For that it was of this form. Notice both of them have the same prefactor, both of them are order alpha square term. So both of them should be included when as far as I am discussing an order alpha square correction. So when I do that, I will get this form, very simple and neat and very tight form. It is relatively easy to calculate. So that is my first energy correction, the first non-trivial order energy correction due to relativistic effects, namely spin orbit coupling and kinetic energy. Now there is one more term which I didn't discuss, and I will not discuss it in detail because it requires full treatment, requires Dirac equation. It comes from something called Zitterbewegung. It's a German term, and it's itself an achievement to know how to pronounce it correctly, and I don't even know how to pronounce it correctly. It basically comes for the uncertainty in the position of the electron, which is order of quantum length, and it turns out to be an order alpha square contribution. So when you calculate that, so this is the Darwin term, this is how it looks like, and when you calculate that to some approximation, it becomes this, because del dot r is basically 4 pi delta q. So this is basically contribution at L equal to 0. Now if you notice, you go back in this formula here, if you plug in actually L equal to 0, these formulas are not valid, because these things blows up. So but what happens in actually L equal to 0 is this contribution comes in effect, because you cannot take L equal to this one doesn't have like the L equal to 0 contribution. So the L equal to 0 contribution comes from this Darwin term. So that is basically all the order alpha square contributions. So when I put all of these, you can show that and plug in the numbers, you can show that 1 by 1s level will go to this this 1s half, and all these higher level like 2s 2p 3s 3p 3d, all these degenerate levels, they will have, because of relativistic effect, the fine structure, they will no longer be degenerate. So they will have their first order correction of order alpha square, and as we have seen that these corrections are all dependent on this j. So this j will give us, and so by the way, for s equal to half you will get this Darwin term, which is this correction for L equal to 0, and you will see that and that's in this order alpha square shift which coming from that. There will be similar order alpha square shift which comes from the j value, like j equal to 3 by 2, j equal to half will have this shift, j equal to 5 by 2, j equal to 3 by 2, j equal to half will come from this kind of shift. So the relativistic effects, basically all these terms, they disturb the symmetry of the Hamiltonian and lifts the degeneracies, and this is the amount of shift which you can compute, and turns out you can measure it like Michelson-Morley did, and they are very accurate. Like that is exactly the numbers you get from the fine structure and the spectroscope. So that is all about the relativistic effects. Now there are further relativistic effects, something called lamp shift. For that you have to take the quantization of photons, and you will learn that in QED course. And also there are hyperfine structures which comes from even higher order correction of alpha to the power 4. But that is not we will not discuss that in this course. Okay. Now the next topic will go to two very important effects called Zeeman effect and Stark effect. Now these two things are the most important, probably the most important discovery in the context of spectroscopy, and the best part is that they are very precisely explained by quantum mechanics using perturbation theory. It is one of the biggest triumphs of quantum mechanics, in fact. And interestingly, these things were discovered way back in 1897. Like Zeeman discovered it in way back in 1897, and it was immediately recognized as a very important effect, and it was awarded Nobel Prize in 1902 within 5 years. That doesn't happen usually. Nobel Prize is awarded in 20-30 year scale. So what he discovered is that these are, let's say, the hydrogen atom spectral lines. If we turn on a magnetic field, a strong magnetic field, you will see these lines are splitting just by magnetic field. Why is that? So there was no explanation, and you know that quantum mechanics was, people figured out quantum mechanics around 1920-25 period, and 1925 was officially the first paper on quantum mechanics. So the explanation came after 1926. So it took like 20, almost 30 years to understand the discovery of Zeeman, and until quantum mechanics appeared, people took it as some mysterious effect which they knew empirically, and it was enormously useful in many different things. So one of the many areas of application of this today is this magnetic field measurement. So basically you can precise in astronomy, it is heavily used, especially in solar astronomy. You can measure the magnetic field of sun, for example, by looking at the shift or splitting of the helium or hydrogen gas spectra of sun, and so on. Like you can measure it for any star and all that. So that is one of the things which is very widely used in precision spectroscopy in astronomic applications. And there are wide range of other applications like NMR and like nuclear magnetic resonance, electron spectroscopy resonance. Okay, I may not be exactly right for the ESR full form. It's practically used in MRI, like the brain mapping and all that, where you basically do a spectra and all that, and Mossbauer spectroscopy and so on. It is a very, very important effect which allows us to understand a lot of things about a system. It is usually any experimental measurement is basically you have an object which you disturb with something and measure the response of the object to that disturbance. Any experiment is that basically. You pass an electric field, you put an electric field, you put a magnetic field, you bombard it with some neutron, and or you bombard it with electron or X-ray or something, and see the response or scattering, what is the scattering happening, or what is the how the system is responding to that disturbance, and or the what you call more precisely as the probe field, and you measure that, and then you know a lot about the system. So that is basically almost any experiment in the world we do. So that is basically Zeeman effect, and it was enormously useful. And after like about 13 years later, after Zeeman effect was discovered, people like Stark discovered Stark effect, which is similar to Zeeman effect, except instead of putting a strong magnetic field, you are putting a strong electric field. And here is like, if you look at the energy level diagram of the Stark effect, you will see that like it is the n equal to 15 and 14, the higher energy states of the hydrogen atom. This is how they split, and that is basically another important discovery of similar nature of Zeeman effect. And again, like both of these, the theoretical development happened much more slowly. For example, in 1901, after these things were discovered, so Voigt tried to explain this using a classical enharmonic oscillator. Like he was that time the idea was that, so there is a little historical account. So that time the idea was this is happening because the electron and atom is vibrating. They are vibrating because of its thermal energy or whatever, and this vibration is causing the, so one should be able to model it as a harmonic oscillator. So people first tried harmonic oscillator, but harmonic oscillator doesn't give you a variety of light, because of course harmonic oscillator have all the energy levels are equally spaced. So you must have to do at least an enharmonic oscillator. So 1901 Voigt tried that using an enharmonic oscillator, but he had no idea about the scales of the problem, like scales and all that, and he was like many orders of magnitude off from the experimental results. So it was clearly not a right thing. So around 1913 actually, the same year where Stark effect was discovered, the same year Bohr came up with his atomic model. So the Bohr-Sommerfeld quantum theory, people also tried to understand this, but this also failed. It was closer, but it failed to explain these effects. It was only in 1926 when the Pauli using matrix mechanics and Schrödinger using the standard perturbation theory. By the way, the perturbation theory we studied today is really Schrödinger perturbation theory. It was this form of perturbation theory was developed by Rayleigh and Schrödinger, and there are various other formalism of doing perturbation theory, some of which I might do if time permits later. Depending on the problem, you can choose a different. There are different. The idea remains same, but there are different ways to do perturbation theory. So Schrödinger applies this perturbation theory, and it was 1926 when people developed a full understanding of this Zeeman effect and Stark effect. It was a very thrilling period. For 30 years, people were trying to understand a problem, which is turned out to be very useful and very interesting, but nobody knew what's happening, and it took like 30 years to fully understand it, only after the development of quantum mechanics. So here is the historical account I already told you about. So you might wonder that why it took so long, because people normally know that electric field and magnetic field are cousins. So if something happens with the magnetic field, that should happen with electric field. People guess that, and people tried to find out for a while, but Stark was the first person to be successful. So both of them won Nobel Prize, Stark and Zeeman, and first person to be successful. And the reason it took long, because the amount of, so for 1 Tesla magnetic field, the kind of effect you can see 1 Tesla, 2 Tesla, the same effect for the electric field you need is much more harder to produce in a lab. Like it needs like 10 kilovolt per centimeter electric field. If you try to do that in this cathode ray vacuum tube, it will cause lot of sparks and discharge. So it took a long time to figure out how to tackle that experimentally, and the Stark effect was discovered almost after 16 years of Zeeman effect. So it was a natural progress of technology and all that, but the theoretical understanding came much later, as I said. So as I said all these things already, that how the Voigt modeled the problem as a enharmonic oscillator without knowing the scales of the problem. So he was doing various fittings, and after that fittings, the results which came were also many order of magnitude off. Also, one more thing is that to discover this effect, there was a bit of luck also, that Zeeman and Stark both chose the very correct gas to see this effect. Like Zeeman chose hydrogen atom, Stark chose sodium atom, which of course they probably didn't land on it at the first time, but they did some trial error and find it. But those are the gases where these effects are also much more stronger. So this is a account behind the things we are studying here. So now let's go to the Stark effect. So let's start with the Stark effect. So for time being, let's ignore the relativistic correction, which I'll come back later. And if I ignore that, so I have the H naught, which is the simple atomic or the hydrogen atom potential, well, it's Z equal to 1, and I put an external electric field which is E, and that electric field will produce will have this effect of E dot R, where R is the position of the atom. That is how it will act on the atom. So now what is this what are the, how will we proceed further? So let us assume that electric field is applied in z direction. So it is E equal to E naught z, and it is constant across the atom, the atomic width, which is a reasonable assumption. And we will also assume, as I said, the electric field is quite strong, such that the fine structure I can neglect the fine structure. I can call it that the fine structure terms are too small to be neglected and can be treated as perturbation further beyond that. So in that sense, if I add that, this whole thing, this equation 1, the whole equation 1 will become 1, will become the H naught, and then the H1 will be, new H1 will be the fine structure terms. So that is the kind of assumption, but now we are doing it like this H naught part we know, and the H1 is the part which we do not know. So let us do the perturbation theory and exploit the cylindrical symmetry which is around the z direction, because the original problem has spherical symmetry, but after I applied an electric field in the z direction, the cylindrical symmetry, like the spherical symmetry, is destroyed, and the new problem has only cylindrical symmetry along the axis z. So how will I calculate the first order correction? The first order correction will be simply applying the formula E psi NLM R bar NLM, which is the remember that it is non-degenerate perturbation theory, and non-degenerate perturbation theory formula which we are trying to calculate here. So in order to evaluate that, you write down the radial part and the spherical part of the wave function of hydrogen atom, and remember that it has this following property, the spherical harmonics has the following property under parity transformation. That is, if I take R2 minus R, this is related, this is how this R and minus R of the spherical harmonic are related, which is by minus 1 to the power a. So knowing that, so let us say I write down this form. So I take the, do the transformation R2 minus R, so put it minus R everywhere. So this is how the form looks like now, but now I can put everything back by saying that the new R, I just rewrite the new R tilde as R for convenience, and I end up with a minus sign, and that can be true only if this whole term is itself 0. You can also directly evaluate it, but the conclusion remains same, that the first order correction is 0. So, and it is for, I can apply this way of writing naively for the non-degenerate perturbation theory, and so that is for the state 100. But for the higher states which are degenerate, I have to apply the degenerate perturbation theory. So let us see what are the, so the non-degenerate perturbation theory for 100 tells us that there is no first order correction. So let us see what happens for the degenerate perturbation theory, which is applicable for other states above n equal to 1. So let us say if I have a state n naught, so any n naught which is not equal to 1, so this will be the term which I have to evaluate as a matrix, because that is what the secular equation will require. So let me take n naught equal to 2. So these are the n naught LM states. So L is like 0 and 1 for n equal to 2, L is 0 1, and for L equal to 0 the M is 0, for L equal to 1 the M is minus 1 0 plus 1. So this will be a 4 by 4, there are 4 states, so it will be a 4 by 4 matrix of the secular equation, where E1 is the first correction. And you can very easily show that out of all these terms, only these two circle terms are non-zero, everything else is 0. How to show that? Very simple, just look at the diagonal terms, they are go to 0 for the same parity reason as the first order Stark effect. Now let us look at the off diagonal term. So I can write the R, because it is E dot R, so I can take the spherical coordinates and write it as R cosine theta. So n naught LM, so Z is basically R cosine theta. So then I plug in all the known forms, all the spherical harmonic forms, which is the radial part and the spherical harmonics in terms of the Legendre functions. And if you turn the crank, like do this simple integrals, which is very easy to see actually, it will have this delta mm prime part, and then there will be a part which is L comma, so a delta L prime plus minus 1. So that is basically a kind of selection rule, it comes also from selection rule, but you can say the first order, the only non-zero terms which are coupled by this are these two terms, and there is a actually very easy way to see this, that why this must happen. And the easy way to see is by noticing that after I introduce this special direction, like if I apply the magnetic field and z direction, so then now the Hamiltonian must commute with Lz because of the cylindrical symmetry, and it must be odd under parity. So this part gives me the M selection or the M rule of the delta M to M prime, because the M is now a good quantum number, and even in the presence of the perturbation, because it has a cylindrical symmetry, so M, the Z direction, the Mz is the good quantum number, and the L selection comes because of the fact that it is odd under parity. So just recall this parity form, because the parity which takes r to minus r, it means this minus 1 to the power L, and these two together without any calculation, you can also, without doing this full calculation, you can also see where these things are coming from. So as I said, the H1, the perturbation here, the Stark effect destroyed the spherical symmetry. So H0 H1 is still symmetric to Z axis, that's the cylindrical symmetry. So Lz is good quantum number. So only M equal to 0 will contribute here. So in this form, as you can see here, the only term where it can contribute with M equal to M prime being, so M can be equal to M prime is this term, given that the fact that otherwise the diagonal elements are all 0. So you get this contribution, and the L selection comes from the fact, by simply observing the fact, if I go back to the Cartesian coordinate instead of the spherical coordinate without using the spherical harmonics, I can write my Hamiltonian, I can write the contribution of this term in this form. So note that this must be invariant under x to x minus x, or the parity transformation. So the matrix elements could be non-zero only if L minus L prime is odd. That you know, again, if we go back to that spherical harmonics form. Also we can show that it is, so it tells you L minus L prime is odd, it does not tell you L minus L prime has to be like equal to 1, like L goes to L prime plus minus 1. That comes from the tensor operator and Wigner-Eckert theorem by doing this. So that I did not teach you Wigner-Eckert theorem yet, so you can ignore that part for the time being, but this is an alternative way to see the same thing, which is which we can directly get here by doing this calculation. Okay. Now with that bit of detail about calculation, we know that these are the only two non-zero terms which will contribute. So you turn the crank, you put the numbers, and you get these two things, this number minus 3e is at a0, where a0 is the Bohr radius. So also notice that in this case, that the only case you can have this linear order of Stark effect, or the degenerate Stark effect equal to 2, is when L equal to 0 and 1, and that is basically of the simplest situation is this, because as you know that the n equal to 2, n equal to 1 case you cannot get it, because the first order or the linear term is 0. So we now diagonalize that spherical, that secular equation or the determinant. Diagonalize means just find the eigenvalues. You will find that 0 0 is still degenerate, plus minus 3e is at 0. So you will see that the degeneracy is partially lifted. So what are this lifted one? It is like M equal to 0 and M equal to 0, which one is coming for L equal to 1 and it is coming from L equal to 0. So these are the two lifted one, and this is the one which is not lifted, as you can see from this cross term. These are the one which is not lifted, and these are the wave function of the non-degenerate part, and that is simply you can understand it is why. It is because of the again in spite of adding the turning on the perturbation, the Hamiltonian still has some symmetry which is along the z direction. That is why this degeneracy is not lifted, but other degeneracy, which is the spherical terms, that degeneracy is lifted. Okay, so M equal to 0 is the spherical term, and this M equal to plus minus 1 has the same symmetry as the Lz. So that degeneracy is not lifted. Okay, so what linear Stark effect does? So it keeps the degenerate lines which are of defined parity as H, and other terms which does not have that parity, they are lifted. So now we can apply the non-degenerate perturbation theory. So also notice that we had to do this degenerate perturbation theory because we have decided to treat the fine structure, and you can argue also that this is a right way thing to do because here the correction with due to Stark effect depends on the electric field. The fine structure doesn't depend on the electric field. So for a strong enough electric field, this is the right thing to do, and the fine structure can be perturbative. But if we choose to do it for a very weak electric field where fine structure is not perturbative, that is a part of the H naught. So after you know the first order correction, you can treat it as a new H naught, and then you treat the Stark effect as a perturbation. Then you can apply actually non-degenerate perturbation theory, because we have seen that the fine structure correction lifts the degeneracy of the problem. So that is how this thing can proceed. For a weak electric field, you can do that. So now you can do the quadratic Stark effect, which is not for the state, because we have realized that the 100 state has no linear Stark effect, but it can have quadratic Stark effect, which in other words the second order correction. So when you do the second order correction, it's order of electric field square. That's why it's called quadratic Stark effect or the non-linear Stark effect. So it's very simple and straightforward to calculate because it is a non-degenerate calculation, and you can show just these two quadratic. Okay, so that's all about Stark effect. Now let's go to the Zeeman effect, which is really a cool subject because there are a lot of rich phenomena associated with the Zeeman effect. So let's start with just a moment.